till now we have seen these all the stuff, whatever I have put here in this slide. And you can see, can you see my screen? Is it visible to everyone?
Yes, sir.
Yes.
Yes.
Oh, okay, great. Okay, so we have seen these all the components that I put on this slide. So if you see, we firstly we started with W. So we have to find the W. We have to find the size of the. So this is like linear classifier that we are going to find it. So once you have W, suppose you got the W, then you have the function. That function is this W into X. So you'll apply that function and you'll get the score. So it's the same thing. From X, then your function, you have W, then we have X, and then you're applying W into X. That will give you the score. Now you have to see like how good your score is doing. And for that, you'll be using the loss, either softmax or SVM. And this loss is like between the prediction, whatever prediction you have from this function, and your ground truth, the actual level. Okay, so suppose you have given X and X belongs to cat. Now your score is saying something else. Maybe it's saying that this is dog. Now there is error. So that will be calculated by the data loss, and you can use either softmax or SVM. Now you also know like what is the advantage of softmax over SVM. So that we already have discussed in the last class. So softmax is like also giving attention on the happier side. So in the case of SVM, if you were happy, then you are not going to do anything. Now your loss would be 0. That means like suppose you are getting the maybe for the actual class, suppose you are getting value 35. And for the other two classes, suppose you are getting 25 and maybe 15. Now these are the scores that you are getting, and I'm putting the margin 1. That means the score of this class should be greater than at least by 1 from other two classes. And that is happening here. So in this case, if you find the loss, you'll be getting 0. So this was the SVM case, but your softmax is not happy even in this case. Softmax wants this value to be maximized. Okay, so it wants this value to reach to the maximum value that it can reach. So that's why like when we are converting into softmax, we are going into probability space. Now instead of working in this original space, score space, we have converted it into the probability space, and there our goal was to maximize the score of the actual class. So suppose you are getting the score of the actual class 0.5 here or maybe 0.6 here, and other class are giving 0.2, 0.2, or maybe it could be like different values also, but total sum is 1. Now this is the actual class. You know that this is the actual class, but you'll be not happy here. Your loss will again, the softmax will or cross entropy will also maximize it. So 0.6 is acceptable because it's like highest one among all these values. But still you want to reach to the 1. So only the 1 is the value which will give you loss equal to 0. That we already have seen in the case of softmax. So softmax will be happy only when you reach to the maximum value for the actual class. Okay. So this all we already have seen in the case in the previous class. Now we have also added the regularizer. So the goal of this data loss is to find the W which can give you loss equal to 0, or maybe it will be close to 0. Okay, so in real scenario, you will be not getting loss equal to 0, but it may reach close to the 0. So you have this set that I already have said in the previous class that suppose we have one set where every W is giving 0. This is the ideal scenario. Okay, if you have this thing, then you can find the smallest W from this. Okay, But again, finding the smallest W was also difficult. That we already have seen in the previous class. Now, even in the actual scenario, you will be not having this type of stuff. Even for getting loss equal to 0 or close to 0, you have to do a lot of things. You have to optimize this W because it is dependent on the data loss. So you have to minimize the data loss so that your W will give you loss close to 0. So this was the goal of the data loss. And then we have added the regularization loss. So now the job, that job of the regularization loss was to reduce or to minimize the value of the W. So whatever W you are going to get for like through this data loss, that means like whatever W you are going to choose here, that should give loss close to 0. But at the same time, like this W should be having low value, and that will be taken care by the regularization loss. So your regularization loss, if you just see here, your regularization loss is not working on the data. Instead, it is working on the W. So this regularization loss is minimizing the value of the W, and that for that we have a lot of algorithms, a lot of methods. Like you can choose L1, you can choose L2, and so on. Now it is clear to everyone. So that's why we add these two terms in the loss function. So now this is your full loss function. So one will be your data loss and one would be your regularization loss. Now is it clear to everyone? Okay.
Sir, one doubt
Am I
here,
audible?
sir. Yeah, one doubt, sir. Here, the function of R of W there in the regularization formula. If I get the W value as 0, 0, 0 in a matrix, the whole function value is 0. In that case, the loss function will not be affected at all.
No. You're saying that if I apply this thing, it will try to make all the values close to 0. That is your question?
Now my
That
question
you're
is
asking?
the W, the matrix, the W is a matrix actually, no, sir. 3 by 3 or the matrix equivalent to the input given. Okay, sir. If that value, if that matrix consisting of 0 values there, if for example very close to 0 value, the function of R of W will always be near to the 0. It will not have effect on the loss function. How does it affect on the loss function?
No, what I'm saying here, you need to see like we have two components. One is your data loss.
Correct, sir.
It will try to make the W close to 0, but at the same time, this loss will also try to make the W optimized so that your loss would be 0. So this is trying to make loss close to 0, and this is trying to make W close to 0. So there is like game between these two. Both are working simultaneously. Okay, so you will be not having the case where most of the W will be 0. That's not possible because in that case, you will be getting underfitted model or the model which will not give you proper accuracy. So you have to take care of these two things. So that's why what I said that I'll give more weightage to this because this is the actual function. This is the actual job. And this is like sidewise job because this is like secondary job because here the goal is to make the model generalized or make the model simple. Like just take the lower values that will make the model simple. So both the things are going simultaneously. So this is like overall loss. So when you go back, these two things will be minimized. So at a time, your this will be also minimized and this will be also minimized.
Okay, it is like converging. 2 points are coming to a conversion point.
Yes. So we have to find in between point where your loss would be close to 0 and your model should be also generalized. That means W should be also having lower values.
Okay.
Okay. Now the next question is we got these all this. Yes, please. Any other question? Otherwise, I'll proceed. Okay. So I assume that there is no question. So now the question is how do we find the best W? How to optimize it? Who will help us to find the best W? But I said that I have to minimize the loss, minimize this loss, data loss. And when I'm going to minimize the data loss, that means, okay. So the goal was to minimize it, and at the same time, again, this part will be also minimized, but main goal is to minimize it. That means we have to find the best W, which will give you loss close to zero, and that W should be generalized W. Now, how to do it? That's the question.
Multiply W with number less than 1.
Multiply W with number less than 1. What will happen with this? How it will give you, like first and foremost thing, like you don't know which one is the best W, or because you started from somewhere, but you don't know which W will give you loss close to zero. This is also in finite space. When I'm talking about this space, finding the W which can give you loss close to zero, this is again in finite space. You don't know where you will be getting the W which will give you loss close to zero. So first problem is like how to find the W which will give you loss close to zero. And the second goal is, that is the secondary objective. That second objective is to get the W which is having the lowest value, to get the W from all the Ws which were giving loss close to zero, the minimum one from that. So okay, so what I said, that to find the minimum W from all of the Ws which were giving the loss close to zero. So first problem is to find the W, to find all the Ws which will give you loss close to zero. Now the second goal is to find the minimum one from that. So this is very, very problematic thing. So for second task, we already have got the regularization term. But then how to optimize, how to find the W which will give you loss close to zero. Okay. So for this, optimization will help you. So optimization is the guy who will give you the way by which you can reach to the W which will give you loss close to zero. So let us understand this optimization through this visual picture. Suppose you are here at this point. Maybe I should take a red one. Suppose you are at this point and you want to reach here. So at this point, whenever I'm saying this point, that means you have some W here. So you have some initial W, you are at this point. Okay, you are you are on the top of the hill. And then your goal is to reach here. Now, how should you move? How should you move from here? You don't know how to move because at the end you have to reach here. That's the final goal. Suppose you have started from here and you took, maybe you went in this direction. You took a step in this direction, or maybe you can take steps in this direction. Maybe you can take a step in this direction. It's like free. You are free to choose any direction. But at the end, you should be reaching here. So suppose you are not following anything. You are just moving naively, just following the naive approach. That means you are just going randomly. So maybe if you are lucky, then you might be reaching here. But that is the, we can say, happiest case. But in most of the cases, you will be not lucky. So if you are not lucky, then you might be go there, here, maybe you trap somewhere here, or maybe some wild animal will kill you. So that is possible. Now, if I go randomly, in most of the cases, I'll be not reaching here because this is This is like forest area, this mountain forest. So it's very difficult to reach here. But goal is to reach here. So this is the maximum point and this is the minimum point. Now let us come to the technical word. So if I'm saying that you started from here, that means you started from some W. So suppose you took one W, random W, maybe from, whenever I'm saying random W, that means you'll be having random values here. So you got one W matrix, random matrix, maybe from Gaussian distribution, from normal distribution. You started with this, but your goal is to reach here. So in this space, you have a lot of Ws. Maybe one W, you have to find that W which will help you to reach to this point. But since you are moving randomly, so it will not give you guarantee that you will be getting the W which will help you to reach to this point. So in the technical manner, what I can say that this is the starting point. That means you have one starting W, and this W will give you some loss, and that is very, very high loss. So that's why you are here. So maybe you have very, very high loss here, and your goal is to reach to the loss equal to or close to 0. This is the place where your loss is close to 0. So you have to find W, the particular W, which will help you to reach this loss equal to close to 0. Okay. So let's see the random, like what I said, that just go the randomly. So if you go randomly, if you follow the random, that means like if you just taking the random W again and again, then what will happen? People already have done this thing. So what they have done, they have considered 1,000 different Ws. So every time, like first time they have taken one W, and then they got some loss, because you know that W will be multiplied with X, that will give you a score. You apply the SVM or softmax, get the loss. So every time he did find the loss, and they have done the experiment for the 1,000 times. And what they achieved, that if I'm doing this experiment for the 1,000 times, that means I'm selecting W 1,000 times. I'm selecting 1,000 different Ws, because I know that this is the W space. And one W, I have to find the W which will help me to reach loss close to 0. Or in other words, I can say like to reach accuracy close to 100%. Okay. So if you are doing this random experiment, what they observed, that they got 15.5% accuracy for the CFAR10 dataset. In the CFAR dataset, CFAR10 dataset, you have 10 classes. Now, if you find the random performance in the random, like if you're just doing the random, then it will be having 1/10 probability. That is maybe 10%. So if you're doing randomly, if you're just selecting random, you're just giving the random class to everyone without multiplying, without doing anything, without multiplying with the W. If you're randomly giving any class to anyone from all the testing samples, in worst case, or this is the best case also, you will be getting this 10% accuracy if you go with the random manner. Now, what they observe, that in this case, if they are selecting the W, like from the 1,000 Ws, they are just selecting the best one. What they observe, that they are getting 15.5% accuracy. So this is the better than this. You can say like this is better than this. That means it's like 5% better than this. So that means this is good accuracy. We should accept it. So even if you are going with random manner, like for selecting the W, if you are selecting 1,000 different Ws, and then choosing the best one, in that case also you are getting 15.5% accuracy. And this is the better than this 10% accuracy. That is the worst accuracy that you can get from this data set. Now we should be happy here. Should we happy here? It's not looking bad. Decent performance. But if you see the SOTA state of art performance, the existing performance from different research papers, you will get to know that they have got performance close to the 100% accuracy. That's 99.7% accuracy. That means whatever we have done here, this is not acceptable. So you can select random W every time. You can do this experiment for 1,000 times, even more number of times. And you may get W which can give you less, or which can give you less loss, or which can give you better accuracy. But you will be not able to get very high accuracy because you're selecting W randomly. Okay. And your SOTA is very far from that. Then what should we do? What should be the best way to do it? I know that I have started from here. I have to start from here. I have to reach here. Now, if I'm following randomly, going randomly, that's not helping me. That means if I'm selecting random W every time, from at the starting I'm here, and now I'm selecting randomly every W, like we are selecting different W at different time. Okay, suppose I'm selecting 1,000 different Ws. That will not help me to reach here. Now, what should I do? How should we proceed? Who will help me at this point? Okay, so I'll give you the answer. The second strategy is follow the slope. So start from here. So this is the starting point. So whenever I'm saying a starting point, you got 1 W here. Okay. You multiply with X. You get the loss. Like you'll get the score here, and then you have the ground truth, you get the loss. Maybe loss you are getting something N. Now you took one step. You just take one step. Start from here, take one step here. And then find whether you are on the right path or not. So every time you have to move and you have to find the slope. The slope will give you the way in which you have to move. Okay, so you started from here. You suppose you took one step. Now at this point you find the slope. Okay, and what you have to do, whatever slope you are getting, you have to go negative of that. That means you have to go opposite of that. Because if you are reaching, if you are coming from here, this is the top, and if you are going down, maybe you have started from here, and you have reached here. Now, if you find the slope at this point, that slope will be negative. That means the direction of the slope would be this. So what is saying? This is saying that the slope, because always your slope will give you the direction of the larger value, and you have the larger value on this side. So this is having higher loss, this is having lesser loss. Okay, so it will give you this direction, but you have to move opposite of that direction. So every time you have to move. So every time you take the step and then see whether you are whether you are moving on the right direction or not. Every time you have to move in that way, and slope will help you. Slope will help you to give you the right direction. So after starting from here, if you reach here, find the slope, and then slope will help you to get the right direction. And if you follow the slope, finally, you will be reaching this point, or maybe close to that point. So let us see this through the example, or before that, let me just give you the formula for the slope. So slope is just very simple. This is like derivative function. So this is the formula of the derivative. Okay, so dfx by dx equal to this limit h tends to 0, f x plus h minus fx divided by h. So this is the h, that is your step. So you started from here, and you took the step. I'll just write here. So this is the starting point, and you took one step here. Or maybe I should write in this way. This is the starting point, and you took this step. And now at this step, you have to find the slope. Okay, so for that slope, what you'll do, you'll find the function at this point minus the function at this point divided by change. That is your step. So that is your h. Okay. Now this is for one dimension, but you'll be doing this thing for multiple directions. So this is like del dfx by dx, then dfx by dy, del x, del y, del z, and like that. So this is sort of partial derivative, because you have a lot of variables. Because in W, we have a lot of values, and every point here is like one direction, and you have to move in these all the directions. You are in the W space, and in the W space you can move in any direction. So these are all the directions. So whatever values we have in the W, those are like possible directions in which you can move. Okay, so that's why whenever you are going to calculate the loss, or whenever you are going to calculate the function, you have to find the differentiate with respect to this, and that's why this is partial derivative, because you have a lot of variables, and this is also called gradient. Okay, so from now onwards, I'll be just taking this name gradient. Okay, most of the times. Okay, so let us understand this through example. This will clear. This will make this whole this understanding of the whole concept that we have discussed. Suppose you got this W. Okay. W is, suppose, let us assume that W is one vector. You have vector given to you. This is the vector, and then, or it could be matrix also, but let us, for the simplicity, let us assume that this is the vector. And you are going to multiply with the x. This is the W. And this will give you the score, the simple funda. Now, suppose you started from the one point. That is your initial point. So I said that you start from here, and then you have to move. Finally, you have to reach at this point. So you started from here. That means you are taking the random values in the W. So this is the initial W that you got from somewhere, or maybe some distribution, maybe normal distribution. You just take all the values from the normal distribution. Now what you can do, you can multiply this W with x, you can get the score, and then you can apply the SVM or softmax and get the loss. Because while training, you also know what is the actual level of this. Maybe the level of this is cat. or it could be something else. Now, whatever scores you got here, you have to find the loss of this prediction with the actual. And these are all the things we already have discussed in great detail. Suppose you got this loss. Okay. Now, you know that this loss is very, very high. The higher loss, you have to move close to zero. But this is high loss. That means you have not reached to this point. That means you are here only. You started from here. Now you have to move to this point. Now what I should do? I'll take the step. But I say that you should take the step. I'll take the step. And suppose I'm taking the step in the first direction, because we have these all the directions. This is first direction, second direction, third direction, fourth, and so on. So we have n number of directions. Now I am taking a step in first direction, and this is the step size. So I took the step. Now if I take the step, that means this W has been changed. It has been changed in the first direction because you have added these values. Now, if this is changed, your loss has been changed. Because again, now this is a new W and you are going to multiply with the X and you will get the score. Again, you will apply the SVM and you will get the loss. Suppose you got this loss equal to 1.25322. Now, can you say me like whether this is the right move or it's not the right move? You took the step in the first direction and you got this loss.
Less.
Your loss is less. It's lesser than this. That means this is right move. It's helping you to reach to the close to the zero. You are moving in that direction. You are on the right path. So whatever step you have taken here, that is helping you to reach to the loss close to zero. That means you are on the right path. So this movement is right. It's correct movement. Okay. Now let's find the gradient. What would be the gradient? So what would be the gradient here? If I find gradient at this point, what would be the gradient? I'll apply fx plus h minus fx divided by h. Now h you know, h is 0.0001. That is this movement in the first direction. What is fx plus h? What is the function that you are looking here? Your function is what? Loss. You want to change the loss. What is this? You want to see the change in the loss with respect to this input or changing in the input. Okay, so whenever you are changing in the input, when we are doing change in the input, what is the effect on the loss that you want to see here? Okay. So your in this case, your function is loss function. Okay, so you are changing and then you are seeing the loss. So your fx is your loss. Okay, so if I write fx plus h, that is this, and my previous, that is fx, is this. So this minus this divided by this, you will get this minus 2.5. So now you can realize here. So whenever you are whenever you are taking the positive step, this is the positive step because you are doing the addition. Whenever you are doing the positive step, you are having the negative gradient. So what is telling that if your gradient is coming negative, that means you should take positive step. So the same thing I was trying to tell you at that time. So when you are moving here, you are going from top to down. At every point, if you are getting your slope, this is the slope. This is also called slope or gradient. So at every point, if your gradient you are getting that is negative, or at every point, whatever gradient you are getting, you should go negative of that. Okay, so you can realize from here. So if you are getting negative, gradient, that means you have to go in a positive direction because you are getting positive. You are taking the positive steps and you are getting the negative direction. Okay, negative gradient. Okay, so let us take one more scenario. Again, I'll come to this. Suppose you took the step in the second direction. So previously, like I was taking the step in the first direction, now I'm taking a step in the second direction. So I took this step. Once I took the step, W has been changed, and now your loss has been changed. So initially you were getting this loss, now you are getting this loss. Now what you feel? This is the right step, or you are not on the right path? Are you on the right path, or it's like
No, sir.
making you
No, wrong path.
this wrong path?
Negative.
If you're on the wrong path, in that case, you'll be getting this gradient.
Positive number.
This minus this divided by the step, it is 0.6. So you are getting the positive gradient. That means whatever step you have taken, that is not right step. So when you get positive here, what it says that whatever step you have taken here, you should take the negative of that. So don't go in a positive direction. You're going in a positive direction. That's why you're missing your path. So you should go in a negative of that. So whenever you are getting positive gradient, that means your step should be negative. Okay, are you realizing it? Because positive step has given you this positive gradient, and that means you're not on the right path, and you should take the right path. So for taking the right path, you have to go opposite of this. Okay. So whenever you have negative, you should go in a positive direction here. Whenever you have positive here, you should go in a negative direction. So that's why I said, like, at every point you will be calculating the gradient and you have to go opposite of the gradient. Is it clear to everyone now?
So how will we get to know that we are reaching like correct amount of steps like we have to take?
Yeah, that all those things will come later. Okay, but just I'm trying to realize it, like how it is happening. So if you are getting negative here, that means your step should be positive, and that we already have seen that when I was taking a step positive here, I was getting negative here, and that means we are on the right path. Now in this case, in the second case, you are taking the positive direction, you are taking the positive step, but you are getting this gradient at a positive, and that means your loss is getting increased. But you should decrease the loss. That means whatever step you have taken here, that's not the right direction. You should go opposite of this direction. That means you have to go negative. Okay. Now, if this part is clear, then I should go for the next point. Now, just take the third direction, 0.78. I made the step. I took a step, and now I calculated the loss. This was the initial loss, and this is the new loss that I got. What you feel? What would be the gradient here?
0.
0. Because there is no change. There is no change. Your loss is it. Please mute yourself. So your loss remains same. Okay, that means your fx is not changing. So if you find the gradient or this derivative, this will be like fx plus h minus fx divided by h, and these two values are same. That's why you'll get 0. So that means this step, whatever you have taken, this is not beneficial. This is just like you started from Manali, you have to reach to the Delhi. And again, you started from Manali and you went to Mandi, and again you came to the Manali. That means like whatever step you have taken, that is not helping you to reach to the Delhi, because you have to anyway, like you have to reach to the Delhi. That is your minimum loss. But you are not. It's that direction is not helping you, because that direction is giving you the constant loss. Okay, so this direction is not helping you. You're getting the loss equal to 0. Okay, so in this way you can find the gradient of every direction. You just take the move, just take the one step and find the gradient. And this gradient will help you to decide the direction. So should I go positive? Should I take positive step or I should take negative step? Like in this first case, you're getting negative value. That means whatever step you have taken, that was the right step. And you know that you have taken the positive step. You can see in the previous slide. Here. So when you are taking the positive, this one, this first slide. So here you can see like when I took the positive step here, I was getting negative gradient here. And that negative gradient was saying that whatever step you have taken, that is the right step, because it was helping you to reduce the loss. So you started with this, now you got this loss. And your loss is getting decreased. That's why you're getting negative value here. Because this minus this. So if this value is lesser, then only you'll be getting negative value here. And if you're getting this value lesser than this, then that is right, no? Because we want to do that. Now, in this case, you were getting this loss higher than this. So this was not the right step. So you took the positive step here, but now you got positive gradient also, because this is the higher and this minus this will give you the positive value. And that's why you're getting 0.6 here. Now, this is saying that the step that you have taken, that's not in a right direction. So you should take negative of that. So instead of taking this positive value, this addition, now you should do subtraction. That means go negative of that. And in the third case, there is no change. In the third case, you are getting 0. So there is no change. So in this direction, there is no improvement. So this is not giving any information. So whatever value you have, you just take it as it is. This value is fine, because there is no improvement in this direction, or there is no decrement. There is no increment. There is no decrement. Just constant value is there. So that's why this direction is not helping you, or this gradient value is not helping you. Okay. So in that way, you can find the gradient, and gradient will give you the direction in which you should move. Okay. Now what you feel? Is this method good for us? Whatever I suggested here, can it do efficiently? Is it efficient method? I said that your gradient will help you to find the direction in which you should move. But is it the efficient method?
So we don't know the magnitudes, like which direction we have to move.
Hello, sir.
Yeah, magnitude. We are anyway.
Hello,
like
sir.
you are. Yeah, please go ahead.
Am I audible?
Yeah, you are audible, sir.
Audible.
I can hear you. Hello. Now you are not audible. So what I was saying that you can, like, this is given to you. You got this thing from the random distribution, normal distribution. You also did this thing, and then you are finding this. So you are taking a step in every direction, and you are finding the gradient. And by seeing the gradients, you'll get to know like which direction I should move. or whatever steps I have taken, whether those steps are right step or I should take the negative of that. So you can decide it based on these gradients. But what I'm saying that is it efficient method to do it?
But what about the case for zero gradient, sir? So there I will not
That's
get any.
fine. Yeah, that's fine. We don't need to move in that direction.
No,
Whatever value we
if
have.
if I get a
Please.
zero gradient there, I will not have any direction to move either in the positive direction or in the negative direction. In that case, what do I need to do?
That means don't move. Don't move in that direction. You have all these directions, no? These are all the directions. Suppose
No,
you are
but
not moving in that, that's fine. That's acceptable. You are moving in this direction. You are moving in this direction. You are moving all in all other directions, and in this direction you are not moving because this is not helping you. That's fine. Like maybe in few directions you cannot move. If you are not moving, that's also fine.
no, sir.
It's
But
not.
for the iteration, for the next
Uh,
iteration, you have decided the sign of the next iteration based on the previous gradient sign. Okay. And for the zero value, what is the sign that you're going to decide for the next iteration? If you keep, and I request you to continue one more iteration after zero, sir.
okay.
Now you got a zero there. Now you got a zero there. What is the next iteration? Please do the one more iteration there.
No. Wait. Actually, this is your new W. Okay. This is your new W. After doing these whole things, after getting all these gradients, now you'll be getting one new W. Because either you'll be adding W plus, either you'll be doing addition here or you'll be doing subtraction here. With the same step size. The step size is same. You are moving equally in every direction. So this is your step size. You move in this direction, you got the gradient, and then you got to know that whatever step I have taken, that is the right step. And then it has been added in this. Similarly, you will take a step in this direction. And suppose you realize at the end you realize that whatever step I have taken, that's not giving me the right direction. That means I am not on the right path. So that means you have to go back. You have to move in a negative of that. So here, like you will be having the next value 1.11 minus 0.00001. In the first case, you will be having 0.4 plus 0.001. So these are the like you're changing the W. These are like your W's are getting changed. The value of the W's are getting changed by the iteration. Next time again you'll take a step after this. Now this is the new W value. So initially you had this. Now you have this value. Now again if you take the step next time, the W, your initial W is this. And then you will be taking 0.00 step. Or a step size could be anything. So every time you're taking the step after getting the new W. My question is it efficient method?
No, sir.
What is the problem here?
So we have to go through multiple iterations, like
Multiple iteration.
again and again.
Yeah. That is required. So even if you train the neural network, you have to go for n number of epochs, n number of iterations.
Sir, we have to compute two times the gradient. One is the current W, and the second time with the addition of all the perturb weight. So it will take a lot of computation.
That means like every time you have to find the gradient. So every time if you are taking the step, you have to find the gradient. This gradient matrix, this gradient vector. You are going to find this gradient vector every time. So whenever you are moving, you are finding this gradient vector. You will be moving in every direction. Na? Here I have just, for the simplicity, I have given this direction, this direction, this direction. But you will be moving in all those directions. And for the every direction, you will be getting the gradient. And then that whole thing will give you the new W. Because after taking step in every direction, you got the gradient, and then gradient like tells you that whatever steps you have taken, that is right step, or you should take negative of that. And suppose you have done all the things, you got new W. Now this is your new W. Now suppose after doing this thing, you got new W. But this is not the final W. Because n is not giving you loss equal to 0. It maybe after doing this iteration, you got something loss equal to 1 point, maybe 1. Still, you have to reach to the 0. Now again, you'll take again the similar type of steps in every directions. And again, you will get all the gradients. Are you getting my point or not? Hello. Is it?
Sir,
Are you able to digest
yeah,
it? Digest.
it is. Yeah, I mean, we're following on, sir. But one question now. See, why we're going back to, and once we decide that okay, we are in the right path, then why are we going back and then again trying another step?
No,
So,
we are
like in
not
this
going
case,
back. We are not going back. Actually, here I'm just giving you the picture of this. But actually, the thing is happening that whenever you took the step, at a time you are taking steps in every direction. I'm just giving you. I'm just showing you like.
Okay,
So,
got it.
but these all the things happening simultaneously.
Sir, why
So
this 0.0001 we are subtracting or adding with only one weightage value?
No, this suppose this is the magic number that we have chosen. You can choose anything, any value here.
Why it is so? See, weightage we have in a array format, or we can say multiple weightage we have, right? So one by one in each iteration, it is getting added or getting subtracted according to the gradient descent with only one weightage value, right?
No, what I'm saying you actually this thing I just for the simplicity I like explain this thing individually. So at a time you're adding here and here. In every direction you are adding this same thing. And for every direction you are getting the gradient here. You are getting the big vector here, the same dimensional vector whatever you have here. And now this based on this information you are deciding like whatever step I have taken, that is the right step or not. Suppose you got this for 2.5, that means this step is fine because this is giving you lesser loss. But suppose in this direction, whatever you have taken in this direction, that is giving 0.6, that means it's wrong. So you should, instead of addition, you do subtraction here. So in the similar way, you will be doing either subtraction or addition, or maybe no change, because at this point there is no change. And this after applying all these operations, you will be getting one new W. Now this W will give you maybe loss something like 1.1 because this is helping you to reduce the loss, and you reach here. Now this is not the final loss. Again, you have to apply these all the things whatever you have done here. Again, you have to whatever W you got here. Again, you have to add the 0.001 or maybe whatever value you want to add here. Again, you do it. Again, find the gradient, and in this way, you have to do this thing multiple times, so that at the end you should reach to close to 0. Now, my question is, my ask is that whether this is efficient method to do it. Now, did you get the stuff now?
Sir,
Clear to
I
you?
know I can. Sir, in this, we are only moving forward.
No, you are moving forward, but again, your gradient is helping you. So if you are moving forward and then if you are not on the right path, like your loss is not getting reduced, then your gradient will tell you, hey, whatever move you have taken, that is not the right move. You should go back. You should move in a negative of that. So you are not moving always forward.
Okay,
yeah, it is being decided by your gradient.
Yes, sir. Sir, I am saying that if like the gradient is telling us to move in some other direction, as we got 0 or something like something which is not which we want. But sir, if there are number of points in the data which create such kind of data that it is only revolving in all the direction, it has to jump out of that problem like that.
No, actually directions are fixed. So this W is having only these many directions. But in that direction, whether you should take the positive move or negative move, that is being decided by your gradient. Because whenever you are taking the positive move and you are getting the lesser loss compared to the previous, that means you are on the right side, you are on the right path. And if that, in that case, if you calculate the gradient, this will be negative. Okay, that means whatever you have taken, that is the right step. So this is negative, then you are taking the positive. But suppose you are getting the positive here, that means whatever step you have taken, that is not giving you the lesser loss. That means you are not on the right path. So when you are getting 0.6, it's saying that no, whatever you have taken the step, that's not the right step. You should take negative of that. That means you should take negative step in that direction. Okay. Now my question. Now what I was asking that whether it is efficient.
Yes, sir. It is efficient actually.
So this is not efficient. So I believe non-linearity features needs to be introduced, right? So that is where the activation functions and other things will come into the picture.
Don't go into those complex scenarios. Okay, just focus here only. Okay, so those are like different things. Okay, so here with respect to this, whatever like gradient you are finding here, is it efficient?
Yes, sir.
How much time it will take? No, how much time it will take to find the gradient?
Sir, it is not efficient because we are taking very small steps. So definitely it will much time consuming.
It's just on one loop, sir. One loop means n. That's all. Time space is n, sir.
Okay, so what you guys are saying that we're taking the slow step, the small step. So that's why this is not feasible. But if you take very larger step, then again maybe it's like overshooting. So you cannot take very larger values. Okay. So again, most of the time you'll be taking smaller values only. But the problem is that this finding the gradient, this is very, very slow. Because you have to find the gradient in every direction. What is this gradient? This is numeric gradient. So you are finding the numeric gradient. That means you are applying this. Yeah, you are taking the step and then you are finding the gradient. So these all the gradients are dependent on the numerical values or values, because this is coming from taking the steps. So this is very, very slow.
So, sir, if gradient,
please.
Yeah, if gradient keep on decreasing, if we go ahead, so one time will come, it will keep on increasing if we go ahead of that position. So we know the correct position where only increasing the single direction values.
Yeah, we are not working in a single direction. Instead, we are working in all directions simultaneously.
Yeah, but that was optimization I was thinking of. We can do if gradient keep on decreasing, and then if we go ahead of that point, it will keep on increasing.
Will keep on increasing.
After that point, if we go ahead, so we know where is the right point.
Yeah. What you're saying, when we will take the larger step, or that's the thing.
Yeah, when we take larger steps.
Yeah, larger step may overshoot. Maybe you want to reach to the Chandigarh, but since you took a larger step, now you're reaching to Delhi. So again, you have to come back. So that's like overshooting. It's like
so we can apply binary search in that
yes, those things are So those things are not. It's not easy to apply binary search and like that. So that's why when we started, then at the starting only I told that whatever algorithms we have, we will be not able to apply those algorithms because this is not the fixed type of problems. So there is no fixed input here. Nothing is fixed here. So that's why whatever algorithms we have in the algorithm book, those algorithms cannot be applied in a proper manner at this for this type of problem statement. Okay. So let us see what's the issue? So the issue is like we have very, very slow gradient. It takes time to find the gradient in every direction because you have to apply loop for I equal to 1, 2, and then in every direction you find the gradient, and then you decide to change this W. Then you will be changing the W. And this is happening for n number of times. Okay. And whenever I'm saying numeric, because I'm totally dependent on this step size, and that's why this is numeric gradient. Now, whenever I'm saying numeric gradient, that means this is approximating. We are approximating the values. We are approximating the gradient. So this is not the actual gradient, but this is like approximated gradient. Because if you change this value, there might be change in the gradient. So you don't know what is the actual gradient. But somehow, based on the changing the values here, or based on the numerical values, we are able to get it. Okay. So these are the two problems. One is like this is very, very slow, and another one is this is approximating the gradient. So what should be the solution here? Can you suggest some solution here? Numeric gradient is slow. Now we have to find some hammer which will help you to come out from this situation, to make this process fast. So what is the hammer here? What we should consider as a hammer in this case? Who will help you? Have you heard this name?
A large step, if we know we have overshoot, then we decrease it by divided by 2 and keep on checking that. I was thinking
but for how many times you'll be doing it?
So yeah, how like
this is again tedious
larger
process.
Values. Yeah.
This is again very, very tedious process. So you will be not like in reality, if I give this thing to someone, he will be not able to do it properly. Okay. So you cannot go with numeric gradient. Numeric gradient is not helpful every time, or in this case. So what is the alternate solution? Have you heard this name? Analytic gradient. You know this, but you have not realized in this way. So analytic gradient is something. So again, let's come to the thing that we wanted to calculate. So we have calculated the loss. This is the loss function. So the total loss was your data loss and the regularization loss. Suppose you are applying L2 regularization here, and this is your data loss, and this is the function of the data loss. Suppose you are using SVM. This is your function of the fxw, that is w into x. And now what you want to do? You want to find the derivative of loss with respect to w. So you want to see that if I am changing the w, what is the change in the loss? And you want to change the loss such a way with respect to w so that at the end it should reach to close to the zero. That's your goal. And that's why you started with numeric gradient. Numeric gradient is like one way to do it. But again, you got limitation there. And that limitation was that this process is very, very slow. And this is like giving you the approximated. It's like just approximating the gradient. So why not we should go for exact gradient? So who will help you? You know that hammer is analytic gradient. And these guys have given this. So actually people confuse like whether he has given or he has given. So that's why they just put these two people. Okay, whenever you just start with the whenever you read the book of this analytic gradient. Okay, so let's see what is this. So now we'll not see, but we'll see it in back propagation. So this is like very simple thing. It's just like if I say you what is the gradient of x squared with respect to x, or what is the derivative of x squared with respect to x, what will be the answer? What will be the answer? If I say you like what is the gradient, what is the derivative of x squared with respect to x, what will you
2x.
say?
2x.
2x.
You know the formula. Analytic gradient is having all those formulas which can be directly applied for getting the actual gradient. So this is the actual gradient that you are getting. This is your function. X square is your function, and you are finding the gradient of this function with respect to x, and that you are getting as a 2x. Now the same thing in the previous case, we were calculating using numeric gradient. So you can also do it through numeric gradient, but that is very, very slow. That's why we have hammer, and that hammer is analytic gradient, which will give you direct formulation of all type of function. So we'll use it, okay, later. And this is very, very fast because you know the formula. Okay, so in summary, we went through this numerical gradient, and what I told you that this is approximating the gradient. This is not the actual gradient. The process is very, very slow because you are going to change in every direction and then you are going to calculate the gradient. So that's why you have to apply loop. And but the good part is like it's very easy to write. You just have to apply for I equal to something, and then you just write the simple formula of the gradient and you will get it. That's the good thing. Now, let's see the analytic gradient. If I go with the analytic gradient, this is exact gradient. If I say what is the gradient of x cube, you'll say like 2x squared. Or what if I say what is the gradient of x squared, you'll say like 2x. So that means you are getting exact gradient or exact derivative. So this is very, very fast. You are just applying the formula. But the thing is like this is error prone. So many times you may make mistake because suppose you have given very huge function, very large functions, you will be having a lot of variables. You may make mistake. Okay, so that's why this is error prone. But the simplest, the simple thing is that when you are finding the analytic gradient, so what you will do, you'll find the analytic gradient, and then you'll check it through the numeric gradient for checking like whether your analytic gradient is correct or not. So that can be checked by the numerical gradient. Okay, so we'll be following this only analytic gradient because it gives the exact gradient, and this is very, very fast. Okay, so with that, this part is done, and this analytic gradient will come later, maybe next class, and then we'll dive into that in a depth manner. Okay. Now, suppose you got the gradient. Now, how to use that gradient? You got the gradient. Now, how should we use the gradient to change the W? Because my goal is to change the W. That's the goal. We got the gradient, maybe del L by del W. This is the gradient. So whenever I'm saying gradient, that means partial derivative. So we got the partial derivative of L because you need to change L with respect to W. So you are changing the W and then see like whether you are getting change in the L or not. Okay. Whether you are getting the positive change in the loss or not. Okay. Now suppose I have used this analytic formula, analytic gradient, and I have calculated it. Now how to change the W? So for this, gradient descent came into the picture. And gradient descent says that if you have gradient, I'll help you to change the W. And this formula is very, very simple. What it is doing, it's doing W new equal to W old minus eta of this del L by del W. Or I should write maybe, okay, this is fine. So what is saying that whatever W, old W you have, you take it negative of eta, this is called learning rate, and into the derivative that you have calculated. Now you can realize it here. It's saying negative here. That means it's saying that negative step you have to take. So whatever gradient you have got here, you just take the negative of that. And same thing. So whenever you were getting positive, like if I just come to the previous slides. So whenever you were taking, yes. So whenever you were getting this negative gradient, that means you have to take the positive step plus. So negative of this, that will give you positive value. So what we have written there, W equal to W new equal to W old minus eta of del W or del L W. So this is del L W. So when you are getting negative, that means this W has to change, has to take the positive steps. That we have realized here. Similarly, if you are getting here negative, if you are getting positive value here, like in the next slide, if you just go to the next slide, you are getting positive value here, and what's saying you should take negative here, because if you have taken positive here, and that's where you're getting 0.6, and when you are getting 0.6, that means you are not on the right path because your loss has been increased. So you have to take negative of this. So what this means, whatever gradient you have here, this W has to take negative of that. So when we have negative here, you should take positive step. When we have positive here, you should take negative here. When we have 0 here, whatever you are taking is fine. 0 means like there is no change. Either you are taking negative, positive is fine. But for the positive and negative, it's giving the direction here. So you have to take the negative of the gradient. That will give you the step for the current W. Okay. So similar thing done in the case of gradient descent. So they have just used the similar idea, and they have given this algorithm. This is the algorithm. So what it says that if I want to get the new W, which is better W than this, then what I have to do, take the old W and then negative and then eta of the gradient. Okay, so you know that you have to go in a negative direction of the gradient. So if you're getting negative value, then you have to go in a positive. If you are getting positive value, then you have to go into negative. Okay, and that is happening here. So that's why this negative sign here. Now, what is the role of this eta? Why we have considered this eta? Eta is your learning rate. If I remove eta, suppose I'm removing eta, does it solve the problem? What you feel? Whether it will solve the problem or what will the problem?
Sir, suppose if the gradient value is too large, it will cross the optimal value.
Yes. Actually, if you just see here, just go to the previous slides. I was doing the small change here. The small change was happening here, 0.0001. But you're getting the large value here. That means your gradient would be large compared to the change here. So if your gradient is coming large, that means you have to multiply this gradient with some lambda, some smaller values, so that it will make these small values. Because you have taken the small step only, but you got the larger values for the gradient. Okay, so this should be also reflected in that formula. So that's why we multiplied with lambda. So lambda into this will come here for making the change of this. We don't want to change this 0.34 with this 2.5. It will give you, like, it will overshoot. That's why I don't want this overshoot. Okay, so what is saying that you just in the step you have to take the small step, but your gradient, whatever gradient you'll be getting, that will be large. Okay, so that's why this eta is there, and we generally take this eta very small. We generally take the value for this eta is very small, like 10 to power minus 3 or 10 to power minus 4, or maybe even lesser than that also. So this is the code for that. So we are just in this line, you can see like we are calculating the gradient. So we are just calculating the analytic gradient. So again, I'll cover this part in great detail next class. So this is giving you gradient of loss with respect to W, because your W's are like variable, because you are going to change the W. So that's why W is the variable, and that's why you are finding the derivative of loss with respect to W. There will be also, like, you will be also finding the loss with respect to bias also, because bias is also variable. So whatever variables you have in the neural network, you will be finding the derivative or this gradient of loss with respect to every variable. Okay. So suppose you got it. Now you have to change the W, or in the similar manner, you will be also changing the bias. So this is the same formula, whatever I have told here. So W weights plus equal to minus step size into this is the way of writing this same thing. So this is same as weights equal to weights minus step size, that is your learning rate or eta, into gradient. Okay, so gradient descent is done. Now you can see here.
So this calculus way of calculating gradient descent you will cover later.
Yeah, I'll cover it later. This will come when we will start.
That dl by dw, it's the way that we have calculated initially, no sir? dl by dw gradient.
Yeah, calculating the gradient with respect to like using the numeric gradient formula.
It is a numeric gradient.
Using the numeric gradient because
dl by dw is a numeric
but
gradient.
now we are. Yeah, actually dl by w is like we are finding the gradient of loss with respect to w. Now we have two methods. Either we can go with the numeric method, or we can go with the analytic method. But so numeric method, yeah.
But in this explanation, you have considered a numeric method here.
Yeah, till now we have only considered the numeric methods to calculate the gradients. But what I told you that numeric is not good, so we have to move for the analytic gradient. So that part will come later, like when we'll cover the back propagation.
Okay.
But here, like, we are assuming that already that gradient is coming from the this analytic gradient. So suppose we are getting it from there, and now we have to use it for changing the W. So this is the formula for changing the W. Okay. So Okay, so I'll stop here. Okay, in the next class again I'll start from here. So any questions? Then
So
please you could
this
ask.
current formula on the screen is for numeric gradient or
Please don't confuse with numeric gradient. Actually, this can be calculated either using numeric gradient or analytic gradient. So you have both the options. But you know that numeric gradient is very slow. So I'll not go with numeric gradient. I'll only go with the analytic gradient. So whatever I'm going to calculate in this, that will be calculated through the analytic gradient, and that will come later. So we'll again go into we'll deep dive into that. But this is simply gradient that you are calculating for the loss with respect to W. That's all. Now, is it clear to everyone? Now, any questions?
Sir, kindly upload all these slides, sir.
Yeah, I'll do it. Last slide I already have uploaded.
Yeah. 2 slides.
Yeah, I'll upload this slide as well.
Sir, just one request, if possible. I mean, whatever we have done, starting from classifying the image, then getting the W at the very start, we are not aware what the W is. We just assume that it's a magical vector or something, and later on, after calculating different Ws, and finally reading up to gradient. So, can you summarize this in, I mean, a 2-minute or something? What is the thing that we are actually finally we will be able to reach after doing all these things?
Okay. Actually,
just connect the dots. I mean, we individually we understood everything. At least I am talking about myself. And individually I understood everything, but I am not able to visualize the larger.
Just wait for next class. So when this fully connected will start, so everything will come there. So, but let me just give you some insight. So actually, our goal is to do the classification. Okay, or maybe it could be some other task also. But here in this case, we are assuming that we have to do the classification. So for that classification, we have to use the linear classifier. But we don't know, like, since linear classifier is having W, and that W is the magic box. So initially, like, we just like our assumption was that somebody already has given that W to you, and that is the best W, which will work perfectly every time. But in reality, that's not the true. Okay, so you have to also find the best W. Okay, so for finding the best W, you need to know, you need to apply some algorithm, and that algorithm is your gradient descent. So this gradient descent will help you to get the best W, which will do good most of the time. That means it will do the classification correctly while testing. Okay, so this is the overall thing. So for that, again, first you need to find the loss, like how bad your W is doing. So you will start from one initial W. So when I started talking about this optimization term, then what I said, that you started from one point, and that point is your W. So you got one initial W, and now you have to traverse in the W space. So you started from here. Now you have to move. You have to move in this space so that you'll be reaching L close to 0. Okay. So that is your optimization problem. And that's why we are going to use this gradient descent. And again, the suggestion was that we should go with the slope method. We should go with the gradient method. We should use the gradient. So again, when I started, then I started with this numeric gradient. Like, can we find the this gradient of loss with respect to all the W's? And then we just started with the numeric gradient, and then we like somehow we realized that now this is the solution. But then what we realized, that
your numeric gradient is very slow, so that will not help you. Then again, you know the solution. That solution was analytic gradient. So can we find this? Can we make this process fast, and getting the exact gradient? So that's your this analytic gradient, which will give you the actual gradient. And once you know the gradient is like the change that you want to do in the initial W. So once you got the gradient, now you have the old gradient, old W. You use this gradient. You use this gradient descent formula where the new gradient would be, a new W would be equal to old W minus eta of the gradient that you have calculated. Okay, so this is the gradient descent. And in meanwhile, I also talked about regularization term. So regularization term is the separate term. It's the goal of the regularization part is not to reduce the loss. Instead, the goal of the regularization was to reduce the values of the W, so that your W would be like whatever W you are going to get, that would be having lower values, and lower values means it will be more generalized. That will be not the overfitted model. Okay, so this was the whole story. In between, several times I assumed that this is the space where everyone is giving, every W is giving loss equal to 0. That was just for explaining that part. Otherwise, in reality, everything you need to do or your model has to do. So you don't know the space where every W is giving loss equal to 0. Even you don't know you don't know the W which is having the minimum values.
Understood.
Okay. So with that, I'll stop here. If any further question I can take, any quick question I can take. Otherwise, I'll stop. Now, is it fine? Like, did you get this whole step?
Yes, sir. It will definitely it will take some time to develop that visual approach of seeing the problems. We will simply walk with you and definitely will reach somewhere.
Yeah. Thank you. Yeah, this will take time. It's not a very easy stuff. But again, when you watch this video, maybe next time, then the things will be more clear.
Yes, my whole point is that we have to develop a problem-solving approach for deep learning.
That you will be able to do. So once we will come to the fully connected, because till now we have not started our like neural
individually we
network.
are able to understand everything, sir. Whatever you are teaching now, individually each concept we are able to understand. We are simply not able to develop that visual pattern in our
That's right. That's right. I'm just giving you all the components.
Yes.
Now these all the we have to just mix up all the components to cook something. So this is just I'm providing you all the components.
Yes.
So I'll come to that part also. How to mix up all these things to get the final outcome.
Okay.
Yeah. Thank you.
Thank you, sir.